Welcome to This Explainer. Today, we're unraveling one of the most epic scientific mysteries of the early 20th century. We're going to trace the absolutely fascinating journey of atomic structure. We'll be zooming all the way down from the old idea of solid, indestructible spheres right into the mind-bending reality of quantum leaps. The way humanity actually figured out what everything is made of, it's honestly nothing short of a scientific thriller. Let's get right into it. So let's start by diving into a massive contradiction that literally had physicists completely stumped for years. Here's the deal. According to classical physics, any accelerating charge has to constantly lose energy. And since electrons are charged particles orbiting a nucleus, which means they are constantly changing direction and therefore accelerating, our atoms should, by all accounts, just self-destruct. The fact that you and I exist right now and aren't just collapsing into a sudden burst of radiation meant the greatest minds in physics had a colossal problem on their hands. To solve this, here's our agenda for today. First, from indivisible to subatomic. Second, Rutherford's unstable nucleus. Third, the quantum revolution. Fourth, Bohr's stationary orbits. And fifth, calculating the quantum atom. Section 1, from indivisible to subatomic. We really have to understand where we started to fully appreciate how far we've come. For a really long time, mainly thanks to John Dalton's postulates back in 1808, we actually thought the atom was the ultimate indivisible particle. Even the word itself comes from the Greek atomio, which literally means indivisible. Scientists genuinely believed matter was just composed of these tiny, solid, featureless spheres with zero internal structure. And sure, it was a neat, tidy model that beautifully explained the conservation of mass, but it was totally blind to what was actually hiding inside. Then, in 1897, J.J. Thomson comes along and completely shatters that neat little idea. By applying high voltage to a gas at a super low pressure inside a cathode ray tube, he discovered these cathode rays traveling in straight lines that were actually deflected by electric and magnetic fields. And because they deflected toward a positive plate, Thomson proved, without a doubt, the existence of a negatively charged subatomic particle. We know this today, of course, as the electron. Boom! Suddenly, the atom wasn't indivisible anymore. It actually had pieces. Section 2. Rutherford's unstable nucleus. But finding that negative electron created a brand new, glaring problem for us. Atoms are electrically neutral overall, right? So where exactly is the positive charge hiding to balance it all out? Well, in 1911, Ernest Rutherford's famous gold foil experiment finally gave us the answer. He bombarded an incredibly thin piece of gold foil with high-energy alpha particles. Now, most of the particles just went straight through, which meant the atom is mostly just empty space. But a tiny, tiny fraction, we're talking about 1 in 20,000, bounced right back. It was literally as if you fired an artillery shell at a piece of tissue paper and it came bouncing back to hit you in the face. This absolutely proved that almost all of the atom's mass, along with its positive charge, is packed into a microscopic, impossibly dense center, the nucleus. Okay, so here's where we hit that fatal flaw I mentioned earlier. Rutherford's model gave us a positive nucleus with negative electrons orbiting it, kind of like planets around the sun. But according to Maxwell's widely accepted electromagnetic theory at the time, charged particles emit radiation whenever they accelerate. An electron orbiting that nucleus is constantly changing direction, which means, by definition, it's accelerating. Therefore, it should be constantly losing energy, its orbit should shrink, and it should spiral right into the nucleus in just 10 to the power of -8 seconds. That is a fraction of a second. The classical Rutherford model completely failed to explain why atoms are stable. Section 3. The quantum revolution. So, to explain why everything around us hasn't just collapsed into a sudden flash of light, scientists realized they couldn't just tweak the old theories. No, they had to throw out the old rulebook entirely. See, classical mechanics works perfectly for our macroscopic visible world, like calculating the exact trajectory of a thrown baseball, where motion and energy are smooth and continuous. But when we zoom way down into the microscopic, invisible world of the atom, those rules completely break down. The behavior of matter at this tiny scale actually operates on discontinuous, discrete states. It's quantized. The real groundwork for this massive paradigm shift was laid out by the photoelectric effect. Scientists noticed something bizarre. Shining light of a sufficiently high frequency onto a metal surface would instantly eject electrons right out of it. But if the frequency was too low, absolutely nothing happened. It didn't matter how blindingly bright the light was or how long you stood there waiting. Nothing. This hinted at something huge. energy wasn't just a continuous, flowing wave. It actually arrived in distinct, discrete impacts. And this perfectly aligned with Max Planck's pretty radical hypothesis from back in 1900. To solve some major issues with black-body radiation, Planck proposed that atoms and molecules just do not process energy in a smooth, continuous flow. Instead, they absorb or emit energy discontinuously in these tiny, definite little packets called quanta. And crucially, the energy of each one of these quanta is directly proportional to its frequency. That gives us the absolute legendary equation E equals h times nu, where nu is the frequency and h is Planck's constant. Section 4. Bohr's stationary orbits. Now, armed with this incredible new quantum toolkit, a brilliant Danish physicist named Niels Bohr steps up in 1913 with a radical new atomic model. His main goal, save the atom from total collapse. And he brilliantly solved the problem by introducing highly specific boundary conditions, basically forcing quantum rules onto the electron. First, he stated that electrons revolve around the nucleus in stationary, circular paths. Now, they aren't stationary, meaning the electron is standing still. They're stationary, meaning their energy is fixed and unchanging. Second, the electron doesn't radiate any energy while in these orbits. Energy is only lost or gained when an electron makes a sudden, instantaneous jump between them. And third, the electron's angular momentum is strictly quantized to integral multiples of h over 2 pi. It's truly amazing when you think about it. The electron is perfectly stable, totally breaking those old classical rules by not emitting radiation, until it experiences an energy change. If it absorbs exactly the right quantum of energy, it immediately jumps up to a higher, farther orbit. And when it eventually drops back down to a lower, more stable orbit, it spits that exact same discrete quantum of energy right back out, often as a single photon of light. This completely explained the distinct lines we were seeing in atomic emission spectra. It all just clicked. Section 5. Calculating the quantum atom. So, having established this completely revolutionary theoretical framework, Bohr actually backed it up with some seriously elegant mathematics. To keep the electron flying in a perfectly stable, stationary orbit without crashing into the center, Bohr applied classical physics mechanics inside his new quantum boundaries. He set the outward centrifugal force of the moving electron, which is calculated as mv squared over r, exactly equal to the inward electrostatic pull of the positive nucleus. These two opposing forces are basically locked in a perfect, never-ending tug-of-war. By taking that perfect balance of forces and then substituting in his new rule for quantized angular momentum, he derived this absolutely beautiful equation to calculate the exact radius of any orbit. It revealed that the very first orbit of a hydrogen atom, its absolute ground state, is exactly 0.529 angstroms away from the nucleus. And notice that the radius actually scales with n squared. That means as you go up in energy levels, the orbits get significantly farther and farther apart. And then we get to the absolute masterpiece of Bohr's work, the energy equation. He calculated the sum of the kinetic and potential energy of the electron, and you have to look closely at that crucial negative sign. It isn't just a weird math quirk. It holds deep, deep physical meaning. See, a free electron just floating infinitely far away from a nucleus is assigned an energy value of exactly 0. The negative sign proves that as the electron gets closer and is captured by the pull of the nucleus, its energy drops below 0. It becomes locked in a stable, bound state. It's essentially trapped. When you plug in the constants for a hydrogen atom in its lowest energy ground state, the math gives us a wonderfully precise number. The total energy of an electron resting in a hydrogen atom's ground state is exactly negative 13.6 electron volts. Meaning, to free that electron from the atom completely, you would have to supply exactly 13.6 electron volts of ionization energy just to push it back up to 0. So Bohr fundamentally solved the massive crisis of the collapsing atom, and yes, he won a well-deserved Nobel Prize for it. He perfectly modeled hydrogen. But here is the massive cliffhanger for you. His elegant, beautiful circular orbit math completely breaks down the second you add a second electron. It really only works perfectly for single-electron, hydrogen-like atoms. The repulsion between multiple electrons actually requires an even more bizarre, wildly complex framework. We're talking wave functions, uncertainty principles, and probability clouds. So as you digest exactly how we saved the single electron atom from totally collapsing, I'm going to leave you with this. What wildly complex quantum mechanics are required to explain the multi-electron reality of the rest of the universe? Thanks for joining me on this explainer, and remember, the closer we look, the weirder the universe gets.